All right. Welcome everyone. So first thing I want to point out is in the last minute of class when I told you all the answers, I told you the wrong answer. The answer was the one that most of you put, which is good to see. The angle was 30 degrees, and I updated the picture here so you can see that. So last class, this was magnetic flux, in case you're like, what is he talking about? We ended last class with finding magnetic flux due to a, is that the right one? No, there we go. It's easier to see now. Magnetic flux. So we did electric flux, we did magnetic flux. Also, so that was a lot. Just want to point that out real quick, and then we'll jump into this. Also, a reminder, when did we finish up last class? We did Ampere's law. We found a magnetic field inside of a wire, specifically at J. You do a bunch of wires inside each other. And so Ampere's law was like Gauss's law, but instead of 3 dimensions, it was 2 dimensions. Instead of for electric field, it's for a magnetic field. But you get to practice those skills of finding what's enclosed, drawing a fake shape around something and finding what's inside of that fake shape. Similar idea to Gauss's law. So just something I want to quickly mention is like, why are we doing this? Are you ever going to do Gauss's law or Ampere's law in your life? No. I can almost straight up tell you all that you're never going to actually do Gauss's law or Ampere's law at any point in your functional career. So why in these classes do we have you do things that you're never actually going to do in your real job? The most important skill I can teach you all is how to think, how to apply these problems. So when we use techniques like Gauss's law and Ampere's law, these kind of quote-unquote tricks that we can do, these will show up in your jobs. These will show up in the various fields you go into. There's kind of like a brute force way of doing it. That's like integrating things. And then there's like little tricks that pop up. If I draw this imaginary loop and I do some things, I can shortcut and solve some problems I couldn't otherwise do. So it's important for us to see that these tricks kind of emerge, and these tricks have processes to them that you need to be able to follow. And so practicing those skills in the context, I can't predict what the context is going to be for you all. You're going to see what I mean later on. Years ahead, you're going to find there's some tricks for doing something. And I can't promise it's going to be a similar context of drawing an imaginary shape around it and doing things. But it's not going to be uncommon for that to happen. So anything I teach you all in this class, there is something we said about learning how electronics work and generators and motors and things like that. That's a pretty easy sell for me to sell that to you all. But honestly, thinking through problems, applying complex steps where you do this and this and this and this, doing enough of that is honestly the most important skill I can teach you all. And you will realize as you go forward in your career, this is something that's not going to be like it's going to be a gradual thing you're going to improve in, and you're not going to even realize how much you improved in it until at some point you interact with people and you realize other people don't have these skills. And it's not because they're any less intelligent than you, it's because you will be practicing this for years, thinking through complex problems, applying multiple logical steps to reach some conclusion. That sounds like a basic kind of thing, but that is what a STEM career is. What is engineering? It is applying logical steps to reach some conclusion. And the key here is you reach that conclusion through known, accurate processes that if I do this, and if I do this, and if I do this, and if I do this, it spits out the same thing every time. That is what logic is. 2 plus 2 is 4. Always. 2 objects plus 2 objects equals 4 objects. So anywho, that's just my sell to you all, and that's true of every single class you all take moving forward. Most of your classes is to teach you the content a little bit, but more importantly is to get your brain practicing the skills of critical thinking within a bunch of different contexts in a bunch of different ways. And so Ampere's law, Gauss's law is one way of doing things, and there's integrals, and that's another way. So many different ways to do logic. So that's my little aside. No one's like raised any complaints about it, but I just think it's every now and then useful to remind you all there's a reason we have you do this, even if it's not clear why. There's a reason this is in the curriculum and things like that. It's been going on for many, many years, and it's not just doing it for the sake of doing it. Yeah?
Do computers use Gauss's law
Yeah, it's a good question. I honestly, so the question was, do computers use Gauss's law and Ampere's law? Maybe. I actually don't know for sure. They might. It depends if there's symmetry. If there's symmetry, they're going to use Gauss's law. If there's not symmetry, they might brute force do an integration of the charge and things like that. But yeah, there is, when I say you all might not even know, this is, people are doing, like, if you're measuring magnetic fields or electric fields, something is doing this. Something is doing this at some point. These are useful quantities for us to determine. In fact, I didn't have you all. So I'm updating the lab, so you're not going to get to see the updated lab. But you all, in one of your labs, measure the magnetic field and use the IOLab to do so. IOLab is that red box that you all use to measure the magnetic field of the Earth. You hopefully remember that for like a few weeks past. Something I'm updating the lab to do, and I'll send out a link to this because I think it's really cool. There's a software called Phyphox, Phyphox. It's a free software. It's developed by a German university. So it's very trustworthy. It's not just some random person doing this. It's a whole university. It's very well developed. This software is super cool. I know this is a tangent, but I think it's worthwhile. Normally I don't go, Phyphox, free software. Highly recommend it. What's really cool about this is your phone has so many sensors in it. Your phone has accelerometers. Your phone has gyroscopes in it. Your phone has magnetic field sensors in it. It has 3 magnetic field sensors, X, Y, and Z, just like the IOLab did. Why? Take a guess. Who can figure out why your phone might have magnetic field sensors in it? It is an electronic, but there's an actual practical application of knowing the direction of magnetic fields. Global positioning system, specifically because your phone needs to orient to know something specific. What is that? What does your phone need to go to do without the internet? It needs to know which way you're traveling. How do you orient your phone in the direction of travel? Compass. So, fun fact, your phone can determine which way north is without being connected to the internet. That is a thing your phone does. If you disconnect to the internet, you can still figure out which way north is. How? Magnetic field sensors. Your phone has incredibly accurate magnetic field sensors. Why am I mentioning this? This app will actually let you access those, which is kind of cool, and you can take measurements and do fun things. It generates graphs just like the IOLab and cool things. The reason I brought this up, though, is it has to calibrate. Your phone is not just measuring the magnetic field through the Earth. Your phone is measuring the magnetic field to do everything around it. It doesn't know what's around it. It just takes measurements. It has to know how to remove those external fields. It has to know to calibrate and remove those fields. Fun fact, your phone uses electricity. If your phone uses electricity, guess what? There's current in your phone. If there's current in your phone, what do current carrying wires make? Magnetic fields. Your phone literally has to account for the current carrying wires inside of itself. Same with, in the case of the magnetometer, it doesn't worry about those. So yeah, your phone is constantly calibrating for the magnetic fields generated both by itself and everything around it. This is something you don't realize is happening all the time. Technology is wild what it's doing. But if you don't know how magnetic fields work and things like that, if you don't know how the calculations work, you're kind of at a disadvantage compared to everyone else. You're not going to understand how things work. Good question. I don't think so. I don't know for sure. The question was, do laptops and things like that have it? I'm not 100% sure, honestly. Your phones need it for GPS. I don't actually know if you can use your laptop as a GPS because it might not have those. All right, great. Complete aside, download this app. Super cool app. If you don't think it's cool, then I don't know what to tell you. You might be in the wrong field. Because it's just data that you have access to. It's super cool. All right, great. Aside, there it is. Magnetic fields. Magnetic flux. This is the same equation for electric flux. Now, I am going to spare you all. I debated on making this I debated on whether or not to actually make you do the integral, but I'll straight up tell you I'm not going to make you do the integral. You're spared that well, it's not suffering, it's fun. You're spared that complexity. So I will tell you that pretty much every problem is going to boil down to when we talk about flux. It's going to turn into B will be a constant, the angle will be a constant, kind of, sort of. The The angle may or may not be a constant. You'll see what I mean. It'll be a constant along the surface, so we can put out the integral. In the area, okay, when I say they're a constant, I mean, you'll see what I mean. They turn into this. They might vary. We're going to see why. But you're not going to have to do the integral. Great. Flux. What is flux? Anytime the word flux is used in any of your classes, it is not just for electric fields. It is not just for magnetic fields. Flux is like the flow of something through something. The rate of how much of something is going through something. So you might see this word flux used in other disciplines and other contexts. I actually don't know for sure. But flux capacitors is nonsense tied together to sound sciencey. But flux is used in a bunch of different ways. Anytime flux is used to describe the flow of like a vector field through some surface. And there's tons of vector fields other than just this. Fluids, there's going to be a flux of fluids. All right, now I'm immediately going to jump to Faraday's law. I'm not going to actually derive Faraday's law for you because it's a law based on observations of reality, and deriving it gets a little... Honestly, anytime we have a law, we can kind of just make the statement it's an observation based on reality. This is experimentally kind of proven, determined. What does Faraday's law say? Faraday's law says that if I have a changing flux, if my flux changes with time, I make something called an EMF, an electromagnetic force, in a wire. Now, when you all see EMF, anytime you all see EMF, I want you to look at the units to help us understand what it is. The units for EMF are volts. Anytime you all see EMF, pretend like it says voltage. Anytime you all see EMF, pretend like it says voltage. I will explain in just a little bit why we don't just call it voltage, but for all effective purposes, it's like there's a potential difference in the coil. And if there's a potential difference, we learned this, current will flow. If there is a potential difference in a wire, a high and a low, current will flow. So, if there is a change in flux, there will be this quote-unquote effective potential. What does this effective potential do? It makes current. Why is this meaningful? We have made electricity. If we change the flux, we make electricity. This is how every single way of power generation works except for solar panels. Wind turbines, generators, turbines used in coal power plants, nuclear power plants. This is the equation that explains how we get voltage. This is the equation that tells us how we generate electricity.
What about something like a car or a plane?
That's a great question. A plane and a car use something, at least a plane, it's called an alternator. It's the same thing. An alternator is just a little mini generator where it uses the spinning of your drivetrain to drive the alternator to generate electricity. This does not explain batteries either, but hopefully that's like, I forgot that one. That one's another way to generate electricity. Okay. So, key takeaways. Even if you forget everything else I said, here's the 2 takeaways from this slide. And I'm going to say more things, but this is the 2 most important things. Changing flux makes an EMF. EMF is like voltage. Changing flux makes an EMF. EMF is like voltage. Now, why do we call this EMF? Why do we call this EMF? This is just an aside. If you don't understand this, don't worry about it. Why do we call it EMF? Say I have a loop of wire, and I change the flux to make this EMF, this electromagnetic force. That is going to make a current flow in the wire. Awesome. Say I wanted to measure that EMF with a multimeter. Say I wanted to take a multimeter, and I wanted to measure the EMF, and I put one probe on one end, and I put one probe on the other end. Because to measure voltage, you need to measure a high point and a low point. If I do this, it's not really going to work. Maybe I actually have to test this. I think maybe you'll get half the voltage. You will not actually get the full voltage. Remember, to measure voltage, you need to measure the high point and the low point. So the question is, where is the high point? Where is the low point? There is no high and low point on this circuit. This is why we call it EMF and not potential difference. There is no high point voltage. There is no low point voltage. There actually isn't any spot on this with a high voltage and a low voltage. It just acts like there is. It acts like there is a high voltage and a low voltage, but in reality, there isn't anywhere you can probe to measure that. So that's what's weird about this. And if you're like, oh, what if I just put the probes like here and here? That doesn't work either because those points are right next to each other. You get a voltage of 0. So this is why we call it EMF. It's not just because we want to make things complicated. It's because it's fundamentally different, but it acts the same. So if none of that made sense, ignore everything I just said. All right. Let's see if this landed. There was 2 main points. Let's see if one of them landed. If I have an EMF in some circuit, what's causing this EMF? We don't care. And there's a resistance R. What will be the current generated? Treat EMF like change in potential. Is it the EMF? Oh, and this is epsilon. This little symbol here is epsilon. It's a backwards 3. That's small. Another Greek letter 3. Faraday's law is not needed here. This is using something, it is an equation that you've learned in the past.
Is there any relation to epsilon naught?
Different. Yeah, I'll mention that. That's a great question. They're completely different. Yeah, that's a great point that I just kind of skate over because I forgot to even think about that, so I appreciate you mentioning it. All right, give y'all 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so basically this question is, if we say EMF is like delta V, they're not technically the same thing, but they act like they are, so we're just going to say they are. If I want to find current and I know resistance, you all need to remember Ohm's law, one of the most important equations. Every single one of you all do need to know Ohm's law in your life. Like, as an engineer, if you do not know Ohm's law, it'll be a little bit embarrassing. It is a fundamental relationship between voltage and resistance and current. Computer science, you should probably still know it. As any scientist, if you don't know Ohm's law, it means you don't understand electricity. Like, it is the most basic equation for electricity. This one in PIV, P equals IV, those are 2 equations you all should have memorized as scientists, engineers, like whatever. Otherwise, you can't do any electrical work at all if you don't understand those 2 things. Whatever. All right. V equals IR. Rearrange this. Delta V over R. Just replace that with epsilon because they effectively act like the same thing. Yay, there it is. Most of us got that. A student asked a great question. Is this epsilon similar to epsilon naught? If y'all remember from way back in the electric field, there's an epsilon naught. These are 2 different things. We are already getting to the point where we're running out of letters. And we use the same letter for multiple things because there's just only so many letters in the alphabet, so many letters in the Greek alphabet. EMF, they're like, I want to use an E. E is taken. Capital E is taken. I want to use a lowercase e. That's also taken. I want to use epsilon. That's technically also taken, but they didn't care. So, it is what it is. Okay. So, this is what I already said to you all, but now it's in writing. This is the 2 most important. This is incredibly important. If there's a changing flux, magnetic flux, it has to be a magnetic flux, so there's an EMF. If there's an EMF, there's a current. That's boom, we made electricity. Now, how do we change the flux? That is the next logical question. If I want to make electricity, I need to change the flux. How do I change the flux? So this one I'm just going to kind of write out for the sake of time. What are the three variables in magnetic flux? We have B, we have A, we have theta. So, what are the three variables? The three variables are shown in flux. I can change the field. I can change the area of my wire, of my loop, or I can change the angle. The angle is the trickiest, not the trickiest one, but like the one that takes a little bit of thought. Reminder, this is theta between B and A. It is the angle between the magnetic field and the area vector. The theta is the most important one. This is the one that we actually change in the real world. When we're making electricity, you can change the other ones, but the reality is the angle is the most important functionally. It is the easiest to change. And we're going to see why as we kind of explore this. You can start thinking about how would I change the angle. And if you just think a few steps on that, and you think about how any kind of source of electricity works, you can figure it out. But we're going to see it together as well. All right. So I can change the magnetic field. Great. Remember, the change in flux is a derivative. So I take the derivative with respect to time of the three variables. If two of them are constant, pull them out. That's all I'm showing you here. In this class, we are only going to change one variable at a time. But that is not a rule. It is not a rule that you only change one variable at a time. You can totally change all three of these at once. It just then becomes a chain rule. It becomes a little bit messier. I don't need to get to that complexity. But it is allowed. There is nothing stopping me. Nothing stopping it in the real world from doing that. All right, so yeah, great. You see the changing angle. You see the changing area. You see the changing field. Just writing it out explicitly. Fairly straightforward. Okay. Circular loop of wire shrinks from R2 to R1. Its radius is shrinking. Why? Who knows? We don't care. Over t seconds, the area vector stays parallel with the magnetic field the entire time. And the magnetic field stays constant the entire time. What is the average induced EMF? I remind you, when we talk about averages, anytime we talk about averages, so I'm just going to remind you all of this. Remember the definition of velocity was dx dt. That's physics 1. If I want V average, remember that we can change it to a delta. We only care about the endpoints when we talk about averages. So that's a reminder to you all about averages. Great. Try the problem. Find the average induced EMF when the radius changes. We go about 30 more seconds. You didn't write it out? Write it out. The solution problem. The equation and all that. If you did not write the equation for flux on your paper, you should probably write the equation for flux on your paper.
Where's the cosine?
That's a good question. What is cosine of theta? What does that angle represent? What's it the angle between? It's the angle between B and A. So So what is the angle between B and A? It doesn't change in this problem. And what does it start as, and what does it end as then? All right, give y'all 5 more seconds. So 5, 4, 3, 2, 1. All right, so if you made a mistake here, it's probably because you didn't write it out. And you'll see what I mean. Now, I kind of ignored the negative sign here. I said, what's the average induced EMF? It actually worked out fine with the negative sign. And that's something you're going to see me doing for quite a while on these. Is I'm not going to really worry about the negative side. When we get about 10 slides further, we're going to start worrying about the negative side. The negative side means something, but mathematically we'll see what it means in 10 slides. So you're going to notice that for now I'm going to be kind of ignoring the negative sign. It exists, but we're just going to kind of ignore it for now. You'll see why in a second. All right, so we're going to find the change in magnetic flux with respect to time. So negative change of flux. Flux is BA cosine theta over delta T if it's an average. Now, my magnetic field is a constant. My angle is 0. Why? Because they're parallel to each other. It says that in the problem. Cosine of 0 is 1. So, boom, that just gets pulled out. Change in area over change in time. If you made a mistake, you didn't think about area. This is a circle. What is the area of a circle? Pi r squared minus pi r squared over time. So the answer here, again, we kind of ignored the negative. There's a reason why. Right now, the negative is not going to matter. It will matter in about 10 slides. Just wait till then. But yeah, if you made a mistake here, you forgot about the area, not just radius. All right, cool. All right, if I had one loop, we just did one loop. We found the EMF. If I had 2 loops, hopefully it's not a big jump to say that I'm going to double the voltage. If I have 3 loops and each gets an EMF, I'm going to triple the. Each one's going to generate a voltage. Those voltages will add. So, if you had 2 loops, you get twice the EMF, twice the current. 3 loops, 3 times the EMF, 3 times the current, so on and so on. So, if I have n loops, you just multiply by n. So this is why whenever they're doing generators, if you all have ever seen kind of any electrical stuff, they have a ton of loops. Because the more loops I can shove in there, you can just multiply how much you make. If you want to make 1,000 times the voltage, make 1,000 loops of wire. And it is much easier to do that than to spin the thing 1,000 times faster. And in fact, you actually don't want to spin it faster for some reasons. We'll see why. All right. Reminder, these need to be insulated. Otherwise, it's going to act like a fat wire, and it's not going to accomplish anything for you. For this one? B pi r squared.
Where'd you get like the delta stuff from?
Average. The definition of average is instead of taking a derivative, you can just take the final minus initial.
And then the B over T on slide 4.
Yeah, that's the definition of EMF, which actually leads, here it is again. So if you want to find flux, you got to find the rate of change with respect to time. The only thing you do here is now is n. If I have multiple loops, that multiplies my EMF generated. 1 loop does it, 5 loops make 5 times as much. You need to make sure it's 5 loops though, i.e. insulating wire, all that. All right, the only thing new here is there's an n in front of it, and this is the one that shows up in the PowerPoint. This is the one that shows up in the formula sheet. Specifically this first one. Great. All right, so let's do a quick problem on this. It's fairly straightforward. 50-turn coil has a diameter of 15 centimeters. It's placed in a uniform magnetic field of 0.5 Tesla, so that the face of the coil and the magnetic field are perpendicular, meaning the area and the magnetic field are parallel. Find the magnitude of the EMF, and the magnetic field is reduced to 0 uniformly in 0.1 seconds. Again, we're going to do the average EMF here. We're not going to bother with the derivative. Uniformly means a linear relationship. Great, so what are we solving for? EMF. What's the equation for EMF? Negative N d flux dt. Now in our case, we're going to look at average, so it's just going to turn it into a delta. It's going to be uniform. We can only do a derivative if I give you a function to actually take the derivative of. So that's going to be something that's going to show up later. We will take derivatives, but we're going to start simple and then do derivatives later. Not that they're really that complex. So delta be a cosine theta over delta t. My theta here is going to be 0. It says that the face of the coil and the magnetic field are perpendicular. That just means that this is the case. The face of the coil is flat. The magnetic field goes through it. If they aren't perfectly aligned, the flux would be 0, and that's not a very interesting problem. So, generally, I will tell you in the problems the angle between the area vector and this. That tends to be the most clear terminology. But in this one, still 0. The magnetic field is not a constant, but the area is, so the area gets pulled out. So in this case, we did the area changing, now we're going to do the magnetic field changing, and it's going to be as simple as it looks here.
Why is it parallel?
It says here that the face of the coil and the magnetic field are perpendicular, so this is kind of the face of it, and it is perpendicular to that, so the area vectors are therefore parallel. It's not the best wording. There's a reason we like vectors. There's a reason we like the area vector. It's a bit more clear, but it'll do the job. All right, the area is pi r squared. So I'm going to write this out. I'm not going to actually put in all the, I'll solve it. It's not that bad. So 50 times pi times 0.075 squared. I gave you diameter, half it to get the radius. Be careful with that. If you're like, why would you do that? That's so mean. In the real world, you almost always measure diameter. If you have a pair of calipers, you're not going to be able to measure the radius. In the real world, you're pretty much always measuring diameter. The equations are almost always using radius. You got to get in the habit of getting it in the way the equation wants. This is a very practical skill. All right, the magnetic field starts at, so it starts at 0.5 and it ends at 0. So we start at 0, or remember it's final minus initial. We end at 0. We start at 0.5, so we put the order that way. It says the magnitude of the EMF if the magnetic field is reduced to 0 in a certain amount of time. Yeah, so it starts at 0.5 and then it goes to 0. And my time here is 0.1. And if you plug in those numbers, it spits out another number. And that's the voltage you generated. Now, this voltage is actually going to be pretty decent. I already solved this problem in my other class, so I know it's around like 4-ish. Why is it so? It is not easy to make a voltage of 4. You may be like, oh, that's so low. I'm applying a field of 0.5 Tesla, which is incredibly strong. Very, very strong. If you put electronics near something that's 0.5 Tesla, it's going to break your electronics because just moving your phone. So fun fact, why do we worry about magnetic fields around electronics? If I have a magnetic field of 0.5 Tesla, it is not uniform in space. It will be stronger close to the magnet, it will be weaker farther away from the magnet. If I move my phone in and out of that thing, what am I doing? I'm changing the flux. Your phone is full of wires. Your phone is full of loops of wires. And if you move those loops of wires through a large magnetic field, such that it varies largely, you're going to induce a bunch of currents in your phone. What are those induced currents going to do? Fry your electronics. They won't explode. They just are very, 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 very thin wires. It doesn't take much current to fry them. This is why we're scared of solar flares. If a sufficiently large solar flare happened, it would cause a very large change in electric and magnetic field. That very large change in magnetic field, when it hit all the wires on all the Earth, it's going to cause a current to get induced. And that current will be very large, and it will fry anything connected to it that's not ready for it. So, fun facts. Yeah. What's the variable where? This one? Delta T.
That's 50?
Yeah, 50. Yeah. 50 turns a wire. No problem. It's always good to clarify. My handwriting ain't perfect. All right, so yeah, we get 4.42 volts.
I have a question.
Yeah.
Why isn't it 0.5 minus 0?
Because it's final minus initial. My final is 0, my initial is 0.5. Yep. So it gets rid of the negative sign for us, not that we really care that much in this problem.
On the equation on the last slide, what's the d? Is that the
Derivative with respect to time. Yeah, so anywho, this is very relevant for all sorts of reasons, not just for electrical generation, but also for we're scared of the sun. All right. Now, what if things are rotating? Yeah.
Sorry, one more question. Do you skip the derivative there, or are we always going to?
It was an average, so we change it to a delta. We will do derivatives, but I have to give you a function to actually take the derivative of. Yep. All right. What we did is stand up and rotating. We did a changing area. We did a changing magnetic field. Now we're going to change the angle. How do you change the angle? By rotating it, by spinning it. This is how every single turbine works. You spin. Now, you are either spinning, in our problems, we're going to be spinning the coils. But in generators, you can actually spin the magnets. You can pick either one. I don't know which one they tend to use. It probably varies based on the design. There's a lot of considerations involved. You just got to spin something. You're either making that field spin around so the angle changes, or you're making the area vectors spin around. You're making one of those two vectors spin. If you want to get real wild, you can spin both of them, but I don't know why you would. They tend to just pick one. All right, so I need to give you all a refresher on rotating objects, because this is stuff you may or may not have learned or may or may not have forgotten. When something spins, we need to describe how fast it's spinning. Instead of using velocity, we use angular velocity. Just think of what the word says. It's the velocity of the angle. It's how much my angle changes every second. Just like velocity is how much the distance changes every second. It's the same idea, both angles. The symbol we use for this is omega. It's a little w. It's a Greek letter omega. It's lowercase omega. It is defined, so if you all remember, this should be a big stretch for you all. Velocity is dx dt. Angular velocity is d theta dt. You can see hopefully the relationship there, why they're both called velocity. The unit is radians per second. Now something that gets kind of unfortunate is radians isn't an actual unit. So when you actually write this unit, you'll often just see it as 1/seconds or hertz. The unfortunate thing is hertz is used for angular velocity and regular and frequency, and they're two different things. I do want to point this out. Angular velocity or angular frequency. They're the same term. So you might see either of these terms. They mean the exact same thing. Same symbol. They're two words, synonyms for the same thing, both W. So I have angular velocity, omega equals d theta dt. This is the one in terms of the angle. You very often sometimes see regular frequency. These are not the same thing. They are not the same thing, and it comes down to the units. Angular velocity is radians per second. Frequency is rotations per second. Both are useful for different things. If I want to describe, for example, your car doesn't give RPMs. It doesn't give it in terms of angular frequency. It's not telling you the radians per second, because most people have no idea what a radian is. What does it give you? It gives you the rotations per minute, but you can convert it to seconds with some simple math. So it's very often that in the real world frequency is reported, but angular velocity is the one that mathematically we generally have to convert it to that for math purposes.
Is that like the same frequency with sound and stuff?
Yeah, and I think there's a typo here. I want to catch this real quick. I have this backwards. So F equals 2 pi over omega over 2 pi. Yeah, this is backwards. Sorry, I caught that last class and I forgot to update it here. You're like, whoa, where did he get that from? Just algebra. And if you rearrange this, you can hopefully see that was a typo there. Why is omega 2 pi f? If I want to go from radians to rotations, I need to get rid of the radians. How many radians are in one revolution? 2 pi. So if I take the radians per second and I divide out the radians, I'm left with revolutions per second. That's where that comes from. So, revolutions and rotations are the same thing. Yep, it's how many times it makes a full circle every second. Now, this should hopefully you've seen this before, but if not, that's why I'm mentioning it here. We need to know these variables for the next few problems. Okay, so my next question to you, to help us with this derivation, we need to write theta in terms of frequency, Because if our theta is changing, then we're not going to write it as theta. We're going to write it in terms of a changing theta. 2 steps here. You need to convert theta to omega, and you need to convert omega to f. Now, something I want to point out is every problem we're going to do, we're going to have a constant omega. We're going to have a constant omega. We're not going to have any angular acceleration. We're not going to have any problems with that. That would introduce an additional level of complexity beyond what we need. So we are assuming a constant angular velocity. That is important for this derivation. Constant angular velocity. I'm going to let you all try this out. Use the equations written on the last slide. And specifically, we went into the frequency and time. You can hopefully tell that all these have time in it, except the first one. All right, give you all about 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, if we have a constant angular velocity, so on the last slide, I told you all angular velocity was defined as this. Omega equals d theta dt. If you have a constant angular velocity, you can do this. You can change it to deltas. And you can rearrange this. And we can use this to basically generate, so delta theta equals omega delta t. And if you just pick your starting time as 0 and you pick your starting angle as 0, it just turns into theta equals omega t. If you can pick your starting point. So you're like, how was I supposed to do that? This is an equation that should look very familiar if we just go to linear coordinates. If instead of angular, we do just regular, x equals vt is hopefully an equation you are very comfortable with. Distance equals velocity times time if you have a constant velocity. Just replace velocity with angular velocity. Replace x with theta. Any equation you all learned with linear variables, you can just kind of swap out v with w's and x's with thetas, and they basically work the same. They do work the same. All right, great. So that's our first thing we're going to do. So we're going to write cosine of theta equals cosine of omega t. This is a very common, so this is any object that oscillates, any object that repeats itself over and over and over and over and over again. Cosine of omega t is key to that. A rotating wheel, a spring that's bouncing up and down, anything, the earth rotating around the sun, anything that repeats itself can be expressed as a combination of cosine omega t and sine omega t. That's a really important, it has to do with harmonic motion. You will see harmonic motion in almost all your old fields. Frequencies are very important for y'all to understand. All right, the last step is really easy. Omega equals 2 pi f. So you just plug that in. 2 pi ft. Notice that the one with the f and the one with the w are not the same. That's a really important point that I need to make to you all. F and w are not the same variable. And it's very easy to mix them up because they have the exact same units. What's the unit for frequency? Hertz. What's the unit for omega? Hertz. It's very unfortunate. Because radians and rotations aren't actually real units, and hertz is 1/2. So I will tell you in a problem, I will say an angular frequency of this, or a frequency of this. If you are not careful, you will use the wrong variable. The units will be the same either way. So be careful on rotation stuff, y'all. This is for all your future classes. Every single person in this room is going to encounter frequencies. Computer science, engineering, physics, frequencies exist. They're incredibly important. A cell signal is just a bunch of different frequencies, like everything. Frequencies are everywhere. This is very important for y'all. So, great, it's that one. This is not just applicable to this. All right. A circular coil within loops in area A rotates with frequency F about a diameter as an axis. I'll describe what that means in a second. The loop is placed such that there's a constant magnetic field perpendicular to the axis of rotation. What is the flux at time t? And what is the EMF generated in the coil, assuming B and A are aligned at t equals 0 seconds, meaning we start at an angle of 0, like we specified previously. All right. So let me just draw a picture of this for you all. It's a coin spinning, like a coin spinning on a table. That's the idea. We got an axis going through it. And then we have a magnetic field. Now, in this case, I told you the magnetic fields start aligned. So we'll have like a magnetic field going into the page. It could have been out of the page. It really doesn't matter. Into the page, out of the page. The area vector and the magnetic field start lined up. We use that to derive the last expression, so we need to keep with that idea. Great. And this thing's going to spin. It's going to spin in place. What's causing it to spin? Who knows? We don't care. All right. We are solving. It is always so great. We drew a picture. What am I solving for? Flux. Magnetic flux. That's part A. So, what is the equation for magnetic flux? Again, we are spared having to do the derivative. So we just BA cosine theta. Now, nowhere in this problem does it say theta. It does say frequency. It says write the flux as a function of time. So you better have a time somewhere in that equation. Where's it going to go? We just derived it. That's what we just did. So hopefully this isn't a stretch. That B times A, and it's going to be cosine of 2 pi ft. This is why I had you all do this. Yay! That's the expression for the flux when you have a changing angle. You do not leave it as angle. You write it in terms of the rate of change of that angle with respect to. If you take the derivative with respect to time, you better have time in there. Otherwise, you can't take the derivative. All right. B. Find the EMF. EMF is defined as negative d theta, or sorry, not d theta, d flux dt. This is a this symbol for flux is phi. P-H-I, it's a capital phi. Just, all the fun. This is phi. It's capital phi. All right, so negative n, d, and we just put our flux in that we just found. Cosine of 2 pi ft dt. B and A are a constant. Pull them out. You all go ahead and do the derivative of cosine 2 pi ft. Try it for yourself. Give you all like 30, 40 seconds. It's a pretty easy derivative. It's what all of you should be able to do fairly quickly. B and A are a constant, so they get pulled out. Derivative with respect to yes. Do it for yourself. Actually do it. Don't just wait on me and use that brain. All right, I think that's enough time. So the B and the A get pulled out. So I pull them out. The derivative of cosine is sine. But before I do that derivative to turn to sine, chain rule. Take the derivative of the inside. What's the derivative of the inside? You just pull out a 2 pi f. And there's a negative sign that's going to come from taking the derivative of cosine, so that's going to get rid of our negative sign. We don't really care about the negative sign currently. I know it keeps getting put here. Give me 3 slides and we're going to see why it matters. And that's going to turn this into sine of 2 pi ft. This is the answer, but if I want to write this in terms of omega, it's going to be n times b times a times omega times time. Oh, no time. That's fine, I didn't put that there. Times sine of omega t. This is another way to write it. They're equivalent to each other. They're the exact same expression. Now the problem was an f, so we should leave it an f, but you could put it in terms of w if you wanted to.
Wait, what is that symbol before the D, A?
And number of loops.
No, it's not like what's that D?
On the bottom? This?
Yeah.
That's a d for derivative.
Oh.
We're taking the derivative.
Oh, right.
All right, so that's the answer. Now, look, there's the answer. It was on the next slide. What happens if omega increases? What happens if I spin my thing faster? Look at this equation and tell me what's going to change. Will it change the voltage? Will it make it go up or down? Will it make the voltage? Remember, EMF is the same as voltage. Will it make the voltage change more quickly? Will it make the voltage decrease? Will it make the voltage change slower, or nothing changes? All right, give me your thoughts. This expression describes how voltage is made in a generator. So this is why this is valuable for us to look at. I have allowed you to pick multiple answers. All right, give you all about 20 more seconds on this. Yeah. There may or may not be more than one. The fact that I let you pick more than one might give some hint to, yeah. But no, I haven't said I don't. All right, we'll close this out in 5, 4, 3, 2, 1. So this expression tells me how my voltage changes with time. And if you plotted this expression with random values, you could actually kind of play around with this. What's important is this term up here. This is omega. So this gets to the heart of this whole sine. Sine and cosine functions are very important for you all to be familiar with. Because again, I don't care what you're doing, you're going to be dealing with frequencies. Everyone, I'd be hard-pressed to find someone in this room that's not going to deal with frequencies. Something I want to point out is this is the expression, let's just call it A naught cosine omega t. This is the expression for anything that oscillates. You all see this before. The term in front of cosine is the amplitude. The amplitude of that wave. This cosine makes a wave that goes up and down and up and down and up and down. The number in front of cosine is the amplitude. Now, we can see here, if I increase omega, I'm going to increase the amplitude. So that means my voltage will, I should have put my max voltage will increase. I should have been a bit more clear there, but let's pretend like this said max voltage increases. The amplitude of my thing's going to increase, and it's going to oscillate up and down and up and down. Now, the inside is the rate of change of that wave. And the higher the inside is, the more rapidly it changes. When does cosine change? It goes from 0 to 2 pi. So if you make that inside reach 2 pi quicker, then it's going to oscillate quicker. So this is a very important thing to understand, what a cosine and a sine function do when you change parameters in them. So it is not only going to make the voltage amplitude increase, it's also going to make it change more quickly. This is a very important design consideration when you're making a generator. You do not just spin the thing as fast as possible, because you run into a problem. Also, if you've all been hearing me talk about oscillating voltage, you might have already made the connection that that's what's coming out of a wall. It's called AC, alternating current. The current goes up and down and up and down. Why? How is it made? It's made by spinning something. And so the last fun fact for you all is all the circuitry in the US runs on 60 hertz. Frequency, I believe that's frequency. 60 hertz. So if you measure the rate of frequency of that outlet, it's going to be 60 hertz. You measure it somewhere in New York, 60 hertz. Somewhere in Texas, 60 hertz. The crazy thing is that all of these outlets are all connected to all the generators. All the generators that are producing electricity are coupled together. And they all must be spinning at 60 hertz. Or at least they must do something after it's connected to make the frequency 60 hertz. Because if one is not 60 hertz, it's going to encounter problems from the others. The others will actually result in some wear and tear of the machine. And if the frequency for any generator gets out of sync, it will actually start to damage the generator. This happened with Texas when they had the big blackout. What ended up happening in Texas is so many houses were drawing power. When you draw power, it starts to make the frequency decrease just due to the consumption of it. That gets a bit more complicated. That's a problem. Generators are made to spin 60 hertz. And if you start having a lower frequency, they start to get damaged because they start to get forces acting on them. So the only solution to that problem is to shut off houses from the electrical grid. Because if you start breaking your generators, there's not really, the comeback from that is a much bigger problem than temporarily losing power for a week or two. It'd be months. To restart the entire grid takes months, which is a big problem. So, fun fact for you all, frequencies, AC, all that jazz.
Wouldn't it also charge slower because it's oscillating?
So it's awesome. So let me show you all a nice little animation of this to help us see this change. So you all can check this out on your own. This is a very simple generator. It's got a magnet on a north end, a south end. The magnets face each other, and you spin the coil around. And we just have the little slip ring here that my currents can kind of slide around. So you can see here the voltage going up and down. Now we're going to learn the direction of voltage in just a little bit. That's the next thing I'm going to teach you. But what I can do over here is I can change the frequency that this rotates. So by increasing it, it's going to spin faster. And you can see when I did that, it made it go up. And it's maybe a little subtle here, so I'm going to go to the other extreme. You can see they're really tight together, whereas when I make it really slow, they get really spread apart. This frequency ultimately determines why the voltage is oscillating. And we're going to learn, literally the next thing I'm going to teach you is how to find the direction of current from this. I haven't taught you that yet. I've just taught you it makes a current. I haven't told you the direction. But you all can actually see here, if you look carefully, the current, when the voltage is positive, current flows one way. When the voltage is negative, it flows the other way. Flip-flops. AC current. Slip ring is it's exactly what it sounds like, as stupid as it sounds. It's a ring that a wire can slip on. So that contact is made, but I can still spin. It's a really interesting problem. If you all try to make a spinning system, it's actually a very challenging thing. Specifically, if you have wires, what's going to happen if you start spinning a system with wires that are literally physically tethered to it? They're going to start getting wrapped together, and that's a problem. I don't know too much about those to say, but you need something that the wires can slip along so that it can actually spin and the wires don't get tangled. Yeah. All right, so direction of current. Now we can finally look at this negative sign. It means something. So my question to you, and think about this for a second, in multiplication, what does a negative sign do to something? It sounds stupid, but it's going to help us understand it. So just think about it, don't yell out the answer. Think about what a negative sign does. All right, so it sounds stupid, but let's understand. If I have a 5 and I and I multiply it by a negative, what does it turn it into? Negative 5, wild, right? If I multiply negative 5 by negative 1, it turns it to positive 5. What have I done? And what the idea I want to get in your head is I made it the opposite. Positives and negatives, you can think about like opposites. So what does a negative sign mean? It means it does the opposite. Let's apply that to this problem. What does this negative sign mean then? It means I'm going to generate a voltage to oppose, to do the opposite of the change. So whatever change is happening here, I don't want it. I'm going to make the opposite to counteract it. That's what that negative sign represents. I'm going to make a voltage to oppose this change. We're going to start to see what that means in practice in just a little bit. But for now, it's the idea of I want to oppose the change. If the change is increasing, I don't want that. I want to do the opposite. If my change is decreasing, I don't want that. I'm going to do the opposite. So this is called Lenz's law. And then we're going to practice this to help make sense of this. The direction of the EMF, the direction of the voltage, which will then cause the current, opposes the change in flux. I am going to make a voltage to oppose a change in flux. And when I say nature is going to do this. This is not something we as humans do. This is just how the world works. When there is a change in flux, a voltage will be generated to counter that. Because it doesn't want it. Why? Because that's how the world works. This is experimentally determined. Why does it do this? We will, at the very end of this PowerPoint, connect it to electric fields. So at the very end, we will connect it to electric fields. It's something you do understand. But for now, this is just how the world works. So this is going to make sense as we apply this, and you're going to need to know right-hand rule 2. You're going to need to know right-hand rule 2 to do this. Just prepare you for that. That's a great question. Is it like friction counters it? They both do oppose it, but for different reasons. Friction is just literally things rubbing against each other. This one, I won't really be able to explain it another way until we get to the end of the PowerPoint, as weird as that sounds. We'll be able to explain this with electric fields at the very, or with magnetic forces at the end of this PowerPoint. All right, so let's look at this problem down here to help understand this. This problem down here is we're going to do a bunch of these examples to understand this. I have a loop going from a place of no field to some field, specifically a field out of the loop. So here is the thought process that we are going to ask ourselves. Am I gaining more field lines or less field lines, and in which direction? How can I counter that? Make a current to do so. That's the 3-step process. And it's written on the next slide, so don't worry. What I just told you is written down. Am I getting more? Because flux, how do I get more flux? More field lines. But the direction of that flux matters. So, when it's up here, and it's in, there's no field here. What's the flux when there's no field? No field, great, no flux. When I come down into this, am I getting more field lines or less field lines? I'm getting more. How many did I have when I was up here? 0. How many do I have when I'm down here? Like 10. I don't know, just if you count the dots. Now, am I getting more out of the page or more into the page? So I'm getting more B out. I had none, now I have some. How do I counteract that? If I'm getting a bunch of vectors going out of the page, how can I cancel vectors going out of the page? Make vectors going into the page. Oppose the change. I am going to, so I'm getting more B out. So I'm going to make B in. I'm going to make this wire is going to make some fields in. No human is making this happen. This is just what nature does. So I'm going to make some fields in to cancel this out. How many am I going to make? however much I need to cancel that change. Now the question is, and this is something you all can do, I have made some B's into the page. How do I do so? How do I make a magnetic field? Current. So my question to you, I have a loop of wire. Which way should current go to make a field into the page? Use right-hand rule 2.5, right-hand rule 2. How do I make a field into the page? Should I go clockwise or counterclockwise? It does. It does matter. Yeah, it does matter. So remember right-hand rule 2.5. Put your thumb in the direction of the field, and your fingers will give you the current that makes that field for a loop of wire. This is the shortcut for a loop of wire. It only works for a loop. So it's going to be clockwise. This is going to make a current clockwise. So how does it make a BN? Current clockwise because of right-hand rule 2.5. So I have shown you all this. I said it in words. The next PowerPoint's going to have it in writing. Because I know that was a bunch of words and that might be hard to remember.
How are we supposed to remember to use 2.5 though?
You do enough problems. That's just the answer. You need to make a field. How do you make a field to do a current carrying wire? Right-hand rule 2. Right-hand rule 2 is how to make the field to do a current carrying wire. If you had a loop, there's a shortcut, which is you throw your fingers in the direction of the current. It makes a field in the direction of your thumb.
I mean, I just pointed my thumb like in the direction of like the counterclockwise or
Won't quite work that way. So we'll do some more of these to kind of practice this. That's ultimately how we figure out any of these things. Yeah. Right-hand rule 2 is how to find the magnetic field to do a straight wire. And then there was a shortcut if you have a loop wire.
You can do that too.
You can do that. It just takes a little bit more effort. All right. Draw a picture. Shock and awe, right? Crazy that we should keep drawing pictures. Draw a picture. There might not always be one given to you. Very important to draw it. Determine whether or not you're gaining or losing magnetic field lines. And you need to identify which ones you're losing. Are you losing into the page or out of the page? So identify whether or not you're gaining or losing magnetic field lines in the direction of those field lines. Oppose the change. If I'm getting more of them, make some in the opposite direction to cancel them out. If I'm losing them, then I need to make more in the original direction. If I'm getting less, then I need to make more. If I'm getting more, then I need to make one in the other direction to cancel it out. Then use right-hand rule. I recommend 2.5 because it's quick and easy to find the direction of current necessary to make that happen. 3-step process. Am I gaining or losing? Counteract the change. What current makes that happen? That's the shorthand of it. Again, this is how we make electricity. This is how things work. There is no shortcuts to this. There is no other way for me to explain this to you that I know of. This is just how things work. If you're like, man, this is complicated. Yeah, the world's complicated. Making electricity was not discovered until the last 200 years. Yeah, there's multiple steps. The world's only going to get more complicated. It's not going to get easier. Am I getting more field lines or less field lines? So we'll see some examples to help us understand the gaining or losing, because there's a bunch of different situations it can be. All right, reminder, right-hand rule 2.5. This is the shortcut. If you want to make a current, if you want to make a magnetic field to the left, and you got a coil, point your thumb to the left, and my fingers are going to coil, the picture shows, and that's the way current's going to flow. If I want to make it field the other way, the current's going to flow the other way. I can't necessarily describe this as counterclockwise or clockwise because the perspective doesn't really work for that. Yep. So we're going to keep using because it's nice and easy. All right. Clearly this is important, so we're going to practice it. So I'm going to give you all a bunch of scenarios, and we're going to even see more scenarios later in this PowerPoint. So this first one, it might not be clear what's going on here because the contrast is unfortunate. That bar should be much darker it's much darker on my page, unfortunately. All right. I have a bar. So I have a loop of wire here. Now it only makes a loop when this bar is connecting it. This right side is open. That is not a loop. So as my bar moves to the left, left. What's happening? Am I getting more or less dots? I'm getting less. Imagine when the bar is a little bit further to the left. Oh, look, there's less dots in my loop. Go through the process. So let's write down the process. I'm going to do that a few times. I'm not going to do it every time because it takes time. I am getting less B out. As the bar moves to the left, I'm getting less magnetic field lines pointed out of the page. I don't want that. Counter that. If I'm getting less B out, what do I need to do to counter that? Make B out. If I'm getting less, I don't want less. I want to keep what I have. So let's think of it this way. If I move this bar to the left, I have less dots now. I don't want less dots. I want the same number of dots I started with. Make more dots. That's the idea here. Whatever is happening, counter it. I want that flux to be the same. How do I do that? I make more dots. More dots. How do I make more dots? Make a current that makes it happen. So my question to you, try this out. How do I make more dots out? Which way should my current be flowing to make that happen? Try it. Right here, rule 2.5. It's real quick. Point your thumb out of the board, and that's going to be the direction. Your fingers give you the direction of current. That's a great question. The loop does not have to be a circle. This loop could be any a square, triangle, crazy. It just needs to be a closed loop. If it's not closed, nothing happens. That's not true. Stuff still happens even if it's not closed. Current just won't flow.
Wait, is the dot the exit into the page or out of the page?
I made more B out. Dot is out of the page. Remember, it's like an arrow getting shot at you. Whereas when an arrow gets shot into the page, you see the feathers at the back.
Oh, okay.
Yep. So, current's going to go counterclockwise. Point your thumb out of the page to make those counterclockwise. I is counterclockwise. Yep. They are. Point your thumb, right hand rule 2.5. Thumb is in the direction of the field, fingers curl in the direction of current. All right, this next one, I had to draw the area vector because it's not very clear here. This loop is like this. It's flat. The area vector points up. This is a loop that's, I don't even know how you would describe this. Kind of like going into the board. Area vector is up. Magnetic field is pointed into the page. Question to you all. If my loop is flat, how many field lines are going through this thing if my loop is flat and my field is up? 0. What's my flux to start with? 0. If I move it to the right, am I getting more or less or nothing? So what happens here? Absolutely nothing. This one, step 1, what's happening? Nothing. The magnetic field is out of the page and my loop is flat. Reminder to you all, it's all about flux. Flux is B times A times cosine theta. If the angle is 90, the flux is 0. I started with no flux, I ended with no flux. Be careful. Am I getting more or less? Depends on the orientation of your loop. So what happens? Nothing. What happens? Nothing. What happens? Nothing. Nothing happens. You will not get any current flowing through that. All right. You all try the next one. I got a minute. Try it. I got a loop going from no field to some field. Am I getting more or less? Counter the change, make a current. I'm getting more dots out of the page. So how do I counteract that? Make a B that's counter that. I don't want more. Cancel it. How do I make that happen? Clockwise. I need to make a field that's in to cancel it. Thumb goes in, clockwise current. Thumb is field in 2.5. All right, y'all. Practice some of these. Next class. We're just going to be practicing this and then applying to some problems. And then we'll hopefully start inductors. Be great. Have a good one, y'all.